projectile motion, right? We talked about projectile motion. How quadratics form. Well, in projectile motion, we have an upside-down parabola model, and we can figure out the height of an object at any given time along the flight of that object. And that's what we've done so far. But we could also use quadratics to model area. And finding, for example, the maximized area of something. We could also use cubics, which we'll get into later when we talk about just polynomials. We can use cubics to model volume of something. So we're going to be using the polynomials here in the next couple sections and chapters. In fact, in chapter 3, we get introduced, for the first time, you guys get introduced to the equation of a circle, if you haven't done any of that stuff yet. Okay, but when we take quadratics and we want to find the x values that give us a solution to the value, whatever that might be, we would take a look at using graphing method or quadratic formula, completing the square, using a square root property, or just generic factoring. So we're going to kind of play around with some of those in the next day or two. So, degree of 2 quadratic. I know quad, you think 4, right? I am thinking 4. So, quadratics have a highest degree of 2, and they have a couple different forms. This first one here is the standard form, probably what we're most familiar with. Does anyone know the other two? What's one of them?
X equals negative e plus or minus the square root of minus 4ac divided by 2.
So that's the quadratic formula. That is true. That's not one of the other forms of quadratic. There are two other, what? Point slope is linear, not quadratic. Yes? It has, there's one called intercept form that we're probably least familiar with. And the other one's called vertex form, parabolic form. Does that ring a bell? And they have different looks. Like this one would be what we call vertex form or parabolic form. That look familiar to you guys? Some of you. And then this one is what we refer to as intercept form, where P and Q are the intercepts, the x-intercepts of your quadratic. So we have this parabola, and that parabola may or may not cross the x-axis. It depends on how it opens and where the vertex is. But we're going to get into that stuff later. We're just kind of reliving some of the things we've previously talked about with regards to quadratics. So our goal here is to try and make a 0 as your solution, as your value, and then finding the x's that allow you to get zeros. And we're going to take a look at the factoring and the square root property today, and then we'll look at quadratic formula, completing the square, and the rest of it tomorrow. All right? So this should be review for us. The zero product property, remember this, is where I end up with a, if I'm talking about, I'm just going to make something up here. If we had that, we had factored one of our quadratics into this, then the zero product property would say, each of those parentheses we would set to 0 and find x that makes that thing true. So yeah, one of my x's is a -1, and the other one is a 3. So those are what we refer to as zeros, because they made the value of the function equal to 0. So this zero product property, absolutely critical for us to be able to do this stuff. But again, it's for two, right? Right? You good? You good? Okay. So, about a little practice. Number 1, what do we need to do first before I can solve it? Oh, it's there we go. We want to make 0 on one of the sides. So if we can move that 4 over, then I can factor it and then come up with my solution. So think about making 0. That's my goal. We want a 0, so that -4 is going to pop over here by adding. And this is one of our, it has actually a special name, this type of quadratic. So you're going to decide, are you an Xbox person, borrow from the cloud person, are you a trial and error person? You're going to decide which one you are. And this would factor into x and x. Factors of 3 and 3 give me the 9. But I want it to be a -6, so they have to both be negative. This is what's called a perfect square trinomial. And they always will become, factor-wise, they'll always become something like that, x minus 3 quantity squared, which means I only have one value of x. That makes this thing true. So here's where we have a parabola only touching the x-axis in one location. So we know that that's going to be my vertex, or my vertex is going. All right, this next one, this again is a good candidate for the borrow from the cloud to the Xbox because I have a leading coefficient that's not a 1. And just as a review for some of us, if we set up this Xbox, remember that whatever your lead coefficient and your variable x goes up in the top, your middle term in the box, and the product of the first and the last term goes down in the bottom, -42. And now you're thinking of factors of -42 that are going to add to a -19. What do we have? Anything work? Say that again. 21 and 2 would work. That's a great idea. So the 21 would need to be negative, and the 2 would have to be positive. So then, I'm saying the word so a lot. Stop saying that. We have 6x minus 21. Now, this is a little weird in the way that we set this up. Then we end up eliminating a common factor, and then it's not so weird anymore. So 6x plus 2. When you look at that, and 6 and 6 gives me 36, not 6x squared. Now that is because in both of these parentheses, I can divide this one by a 3, and this one I can divide by a 2. And we'll be left with a 2x minus a 7, and a 3x plus a 1. And now this would be equal to 0, because there's what 6x squared minus 19x minus 7 actually looks like, factored form. And then my zero product property set each of them equal to 0. And we get our two values. X is equal to 7/2, and x is equal to -1/3. Yes. So trinomials, we think about factoring using a trial and error, whatever. But it's not a trinomial. I wonder if I can still use this Xbox thing if it's not a trinomial. But for 3, I have something I need to do first. What do I need to do? Careful now. Careful. What do we want on one side of the equal sign? We want a 0. We want a 0 on one side of the equal sign. So we're going to, I leave my leading high power, my second degree, I'll leave that positive. So we're going to bring the 2x squared and subtract 3x. Now I'm ready to go. All right, so but what do I do at this point? What could I do? I can take out an x. GCF, is that what you're going to tell me about? Could I do the Xbox on this problem? Yeah, I could. I could still do the Xbox. It's just that my number down in the bottom, this -42, would actually be a 0. I can still Xbox it. But it's easier when you do not have the constant value, the c. It's just think about pull out a GCF. It's usually going to at least be an x. So pull out an x from this thing. You're left with a 2x minus a 3. Now I have zero product property again. And oftentimes, this lone x, the one that's hanging out in front of the parenthesis, gets left out. It gets forgotten. That is a factor, which means it can be set equal to 0, which means the answer would be x equals 0 for that particular. So don't forget, the lone variables that are hanging out. And even if there's a 2 in front of that x, 2x equals 0. Still divide by 2, you get x equals 0. So zero product property. Add 3, divide by 2, and I get those 2. That's my solution. So that's just review of our factoring, coming up with our answers here for these standard form quadratics. Got anything for me here, question-wise? Or just review, right? Yeah. All right. This, we will use the square root property when the bx part of the quadratic is not there. So if there's no b term, this is a great time to use square root, because undoing a squared thing means involving a square root. That's why it's called square root property. Could I do the x box? Yes, I could do the x box on this. But it's just faster to do the square root property. So recognize it. When there's just x squared, no x term, set it up to get x squared by itself, and then take the square root. How many answers will I get, by the way, when the square root is taken of an x squared? 2. So don't forget, you'll always get a positive, negative solution for these. Sometimes they're going to be simplified radical form, which means it's not a perfect square that you're taking the square root of. And I don't want you to convert it to decimal. I want you to leave it in simplified radical form. Correct? Now, unlike the last problems that we were doing where we made a 0 on one side, we actually don't do that with these square root properties. We put the constants on the other side, divide out any coefficients, and then take a square root. So number 1 is already set up for us to do that. So I just divide out my x squared by this 2, and I get x squared equals 7. And then I can take the square root. So here's where I want you to leave your answer as plus or minus the square root of 7. Square root of 7, I cannot do anything simplify radical form with that. So that's as simplified as it gets. And that's the exact number versus me punching it in the calculator and getting 2.4, which isn't exact. It's probably even irrational. So what are we going to do on these? Well, simple little things. We might forget to do the plus or minus. That's probably the most common mistake. Forgetting to make a 0 on one side. Number 2, this is a unique one that there is a easier way to do number 2, and there is a more, not hard, but a longer way to do number 2. So what, again, I want you to recognize is, do you have a situation where you have some x squared value, and then there's no x value, and that's what is happening here for number 2. I can still use the square root property on this. Now, what do you think some folks are going to do on this problem? Give me a chance. Yes, James.
Subtract 4 from both sides.
You mean you're going to subtract the 4 on the right to the other side?
No, the 4 on the left.
So that means add 4 to the other side? Okay, so we're going to add 4 to the other side. All right, and then what? What would you do? All right, then people would divide by 2. That's a good idea. X minus 3 squared is equal to 4. All right, and then what?
Square. Not square, I'm sorry. Square.
Okay, this is exactly what I do want you to do. What I thought people might say is, oh, hey, wait, let's take x minus 3 squared and expand it out to x squared minus 6x plus 9. If you do that, you've created more work for yourself. Why do that? When I can get something that is squared by itself, take a square root, and now my answer just becomes plus or minus 2. And now I take 3 and I add it over there. So 3 plus or minus 2 gives me x equals 3 plus 2, and x equals 3 minus 2, or x equals 5 and 1. That's a whole lot faster than me saying 2 times x squared minus 6x plus 9, 2x squared minus 12x plus 18. minus 4 is now 2x squared minus 12x plus 14. Minus another 4, 2x squared minus 12x plus 10, and then having to factor that with my box. Yes, ma'am?
I thought you couldn't square root things if they were like x minus 3 together and stuff.
You thought I couldn't what now?
You couldn't, you're allowed to square root things if they're together like that.
Okay, okay, you're wondering about this x minus 3 and then the square thing? Okay, if I have a binomial, and that binomial is being squared, there's nothing else multiplying by it, it's by itself. You think of this as like the square root of x. Binomial, the x minus 3 is like my giant x here. And so I can take a square root of this and end up with just what's on the inside. I think what you might be thinking of, tell me if this is what you're thinking of, is a problem like this. Are you thinking of a problem like that?
Yeah.
And then saying, is the answer 2x plus 4y? In that case, you are absolutely right. I cannot, because 4x squared plus 16y squared is married. I can't, they are not factors. See, in this form, I've got a factored form. In this form, I don't. So I can't just simply pull out the perfect square from those pieces. The actual answer to this problem is factor out a 4, be left with an x squared plus a 4y squared, and now 4 is a factor, so a 2 can come out, and I'd be left with x squared plus 4y squared. Got it?
Yeah.
Is that what you're thinking of? It's a good question. All right. Let's get rid of that. Isn't it so exciting? All right, why don't you guys knock out those two for me? 3 and 4 real quick. All right, so we get the plus or minus squared. Can I leave my answer like that? Why not? What do we not like to have in denominators? Huh? Can I have square roots? And right now, this is the same thing as me saying plus or minus the square root of 3 over the square root of 2. So I got to get rid of that square root of 2. How do I do that? Starts with an R. Repossess. Yeah, rationalize. We rationalize, which means, let's undo. We want to make down in the denominator, we want to make a perfect root. In this case, a perfect square root. There you go. Multiply by the square root of 2 on the top and the bottom. And that gives me a square root of 6 over 2. And now, that's my answer, plus or minus that. So don't leave radicals in the denominator. All right, who's got 4 for me? Braulio had it. We just go with Braulio. Yeah. We're going to go with Braulio. All right, so what did you do there, Mr. Braulio? Subtract 27 divided by the 3. We see a little bit of an issue because we're taking a square root of a negative number, but we know how to deal with those. Negative, so here's what happens. The square root of a negative 9 is the square root of negative 1 times the square root of positive 9. The square root of negative 1 is I. The square root of 9, we know, is plus or minus 3. And so we can just write it like that. So if you have a negative inside, an I automatically pops out. Well, hang on, let me rephrase that. If you have a negative inside of an even root, if it's an odd root, it's okay. But if it's an even root, you got to pull an I out and then be left with whatever you're taking the square root of. Like that. All right, what questions do you have? Is this pretty simple? Should we go on and keep going? I think we should keep going. Complete the square today, huh? What do you think? You want to do homework? So tomorrow we're going to smash the other 2 days in? All right. You really want to do that? All right, here's the, let's see, we need to talk about anything here. Well, having a conversation. Make the square root of x minus 3 an imaginary number. All right, we want to find the values that make that happen. So, let's put our thinking head together here. If I want an imaginary number out of this answer, what must be under the square root to create an imaginary number? Negatives. I want a negative underneath this thing to make imaginary numbers. How do we use inequalities to show negative numbers? What do we like to see? That's a good one. What inequality would I set up to say I've got a negative? Bingo! Did you guys hear her? Of course not, because she whispered it. She said x is less than 0 would make negative numbers. Brilliant. So what we do here is if I want this square root of x minus 3 to become imaginary, I must say that x minus 3, whatever it is, has to be less than 0. So now I've taken a square root problem, specified by either saying positive, meaning greater than 0 or equal to, or less than 0 to specify negative. Now I am determining the kind of answer that I can get underneath that radical. This is just review from what we did the last couple of days, right? What's the answer to this? Yeah. If I just add the 3 over, don't I just get this? And in our notation, we wrote it like that. If we're using interval notation, if we're using IB notation, we would write it like this. Do you remember this? You guys remember this? Explain that. Like, how come it's okay? Think about, we just said that underneath here, if I have a negative, I'll get an imaginary number, right? So think about what values of x are going to be able to give me negative numbers. Yeah, anything less than 3, right? So we specify that here, that I have to be negative, meaning I have to be less than 0 to make a negative number. I want x minus 3 to become negative. That's how we're going to do that. So IB notation, remember that parentheses are the same thing as outward brackets. And if it was a bracket, then it would face inward. Meaning, if the problem was this, in the IB notation, it would look like negative infinity to 3, and then this time I would close around 3. You can never close around the end or the this end. Infinity, because I can never be infinity, right? Does that make sense? All right, so that was unique. So then, how about this one? What are you going to have to do now? We want to make it become real. So now I want positives underneath that radical. So thinking about the phrase that I have. Real number means I need to be this. An imaginary number means I need to be this. What's it going to do to make imaginary? What's it going to do to make it real? IB notation. There it is. All right, so we really didn't use any square root properties or anything like that, but we're just talking about being aware of what's underneath our radicals and what kind of radical it is. Even radicals can't have negatives, odd radicals we can, so just got to be aware of that. Anything on those two?